Imagine floating weightlessly through the vastness of space, your eyes adapting seamlessly to darkness, your lungs effortlessly extracting oxygen from a controlled, sparse atmosphere, and your bones no longer weakening from the absence of gravity. This isn't science fiction, it's the astonishing reality of how the human body might evolve to conquer the stars. But what exactly will it take for humanity to become true spacefaring beings? How will space travel reshape our biology, our anatomy, and our very existence? Our journey begins with a surprising fact: the human body, perfected over millions of years for life on Earth, is shockingly ill-equipped for space travel. Right now, astronauts returning from extended missions suffer from weakened bones, impaired vision, muscle atrophy, and even altered genetics. But as humanity stands at the brink of permanent off-world colonization, Mars colonies, lunar habitats, and deep space exploration missions, the question becomes urgent: how will evolution help us overcome these challenges? First, let's tackle gravity, or rather, the lack of it. Humans have evolved under Earth's constant gravitational pull, which shapes everything from our bone density to the functioning of our circulatory systems. Remove gravity, and the consequences are immediate and profound. Astronauts lose about 1% of their bone density per month in space, leading to a dangerous condition similar to osteoporosis on Earth. But imagine a future human evolved specifically for zero or low gravity environments. Scientists theorize that these humans would have lighter, less dense bones reinforced by unique bioengineered cellular structures, bones not dependent on Earth's gravitational pull to stay strong. Next comes muscle adaptation. Today, astronauts in space must exercise rigorously, spending hours each day fighting muscle atrophy. Without this constant effort, muscles waste away rapidly, leaving individuals weakened and vulnerable upon their return to Earth. Future humans might evolve specialized muscle fibers, highly efficient and capable of maintaining strength with minimal exertion, reducing the need for constant exercise. These supermuscles could be powered by novel metabolic processes, optimized to conserve energy and nutrients. Perhaps one of the most intriguing evolutionary changes involves our cardiovascular system. In zero gravity, our hearts become, well, kind of lazy, shrinking in size because blood flows effortlessly without gravity's pull. Long-term space travelers could evolve a cardiovascular system optimized for a microgravity environment, a smaller, more efficient heart with blood vessels engineered to prevent pooling of fluids. Additionally, we might develop superior valves and circulatory adjustments to regulate blood flow without Earth's gravity, eliminating the dizziness and fainting astronauts often experience upon return. The human immune system, honed by Earth's diverse microbial environment, also faces drastic challenges in sterile, controlled space habitats. Astronauts often return with compromised immune responses, more susceptible to infections. To survive prolonged periods in space, future humans might evolve an immune system radically different from our own, possibly enhanced by symbiotic microorganisms genetically engineered to thrive in space. These beneficial microbes would support our health, effectively boosting our defenses against pathogens unique to off-world habitats. Another profound change could occur in our respiratory systems. Earth's atmosphere, rich in oxygen and perfectly balanced for life, contrasts sharply with the artificial, tightly regulated environments of spacecraft and planetary colonies. Evolutionary pressures in these controlled habitats could lead to the development of extraordinarily efficient lungs capable of extracting higher amounts of oxygen from thinner atmospheres. Over generations, respiratory structures might evolve to become more compact yet significantly more powerful, allowing future space travelers to survive comfortably in environments we currently find inhospitable. Then there's the fascinating evolution of our sensory organs, especially our eyes. Vision problems currently plague astronauts due to fluid buildup caused by microgravity. Future space-adapted humans could evolve specialized ocular structures, perhaps deeper-set eyes, modified retinas, and adaptive lenses, capable of maintaining sharp vision despite fluctuating fluid pressures. These space-evolved eyes, might even see a broader range of electromagnetic radiation, providing superior visual perception in the darkness of space. Let's also consider psychological evolution. Extended isolation in confined habitats poses immense mental health challenges, with astronauts currently experiencing increased stress, depression, and anxiety. Could humans adapt psychologically to thrive in these extreme conditions? Scientists speculate future humans might evolve enhanced neurochemistry, resilience to psychological stress, and a predisposition to cooperative and community-oriented behaviors critical for long-term survival in isolated colonies. Skin, our largest organ, would also undergo significant evolutionary shifts. Space exposes humans to increased radiation levels, vastly exceeding Earth's protective atmosphere and magnetic field. Future generations could develop radiation-resistant skin, thicker with melanin-rich layers, or perhaps a novel biological pigment entirely capable of absorbing and neutralizing harmful radiation. Enhanced cellular repair mechanisms would quickly repair radiation damage, dramatically reducing cancer risks and enabling prolonged exposure to harsh space environments. But how would reproduction and human development adapt? Human pregnancy and fetal development heavily depend on Earth's gravity. Experiments suggest microgravity profoundly affects embryonic development, posing severe risks. Yet future humans might evolve radically new reproductive strategies. Perhaps gestation periods would shorten dramatically, or embryos might develop enhanced genetic stability and accelerated cellular growth mechanisms specifically adapted for microgravity. At the genetic level, evolution for space might involve rapid and targeted mutations through advanced genetic engineering. Instead of waiting millions of years for natural selection, future humans could deliberately alter their DNA, integrating genetic sequences from extremophiles, organisms thriving in Earth's harshest environments, to confer resistance to extreme cold, radiation, vacuum, and other space-related hazards. These genetic enhancements would accelerate evolutionary adaptation, creating a new human subspecies perfectly suited for life beyond Earth. Imagine a human colony thriving effortlessly on Mars, their biology fundamentally distinct from ours, yet undeniably human. They move gracefully in Mars's lower gravity, their bones and muscles optimized for efficiency, their immune systems robust against alien pathogens, and their bodies resilient to extreme environmental conditions. These evolved humans symbolize a future where humanity transcends Earth's limitations, becoming truly interplanetary beings. This incredible transformation isn't merely speculation, it's a compelling vision of humanity's evolutionary destiny. The ongoing advancements in biotechnology, genetic engineering, and space medicine hint that such evolutionary leaps might occur sooner than we imagine. Space exploration isn't just a technical challenge, it's the next frontier of human evolution itself. And as we step boldly into the cosmos, we are not merely travelers exploring distant worlds, we are the architects of our evolutionary future, reshaping what it means to be human. The human body, shaped by Earth's gravity, atmosphere, and ecosystems, stands poised at the precipice of radical transformation. As space travel becomes commonplace, evolutionary pressures will carve humanity into beings optimized for life among the stars. Our bones, muscles, organs, senses, psychology, and genetics will adapt, evolving in astonishing ways we can scarcely imagine. And as we gaze at the infinite cosmos, we realize that evolution hasn't ended. It's just beginning a thrilling new chapter, one that propels humanity into the limitless expanse of space, forever changing who we are and what we can become. As humanity continues its ambitious quest into the cosmos, profound evolutionary pressures will also reshape our digestive and metabolic systems. Presently, astronauts rely on carefully curated meals engineered for nutritional efficiency, yet prolonged space travel demands even greater physiological adaptations. Future humans might evolve extraordinarily efficient metabolisms capable of extracting maximum nutrition from minimal sustenance. Imagine digestive systems enhanced by symbiotic gut microbes specifically engineered for space, rapidly breaking down nutrient-dense, compact foods designed for extended journeys. These evolved metabolisms could enable humans to sustain themselves for months or even years with dramatically reduced calorie intake, essential for deep space missions where resource resupply is impossible. Furthermore, hydration would undergo, some remarkable evolutionary changes. Water, which is currently heavy and pretty expensive to transport, might actually become less critical thanks to evolved physiological efficiencies. Humans might develop cellular mechanisms capable of drastically reducing water loss, recycling bodily fluids internally to maintain hydration with just minimal external water intake. Specialized kidneys and advanced metabolic pathways might ensure the body conserves water with extraordinary efficiency, reducing dependency on external supplies, which would, honestly, revolutionize long-term space habitation and travel. Even sleep, which is an essential yet kind of cumbersome aspect of human biology in space, could witness a pretty profound evolutionary transformation. Extended space missions demand optimal alertness and, minimal downtime. Future humans might evolve to require significantly less sleep, maintaining full cognitive and physical functionality with just brief, intermittent periods of rest. Enhanced neurological adaptations could facilitate rapid transitions between wakefulness and sleep states, allowing astronauts to really maximize productivity and responsiveness during those crucial mission phases. The sensory experience of living in space will undoubtedly exert some strong evolutionary pressures on our auditory and vestibular systems. Right now, astronauts often suffer disorientation and motion sickness due to disrupted signals from their inner ears in microgravity. Future humans might evolve refined vestibular systems, specialized structures within their ears, and enhanced neural circuitry to maintain impeccable spatial orientation, balance, and motion perception without Earth's gravity. Such adaptations would allow seamless navigation within spacecraft and extraterrestrial habitats, basically eliminating debilitating nausea and disorientation. Moreover, the very structure of the human brain might adapt profoundly. Space travel demands heightened cognitive functions, superior spatial reasoning, precise calculation skills, and exceptional multitasking capabilities. Future humans could develop larger, more complex neural networks specifically optimized for space travel's demands. Enhanced memory, advanced problem-solving skills, and rapid decision-making abilities might become commonplace, fostering a generation of humans inherently attuned to the intricacies of navigating the cosmos. Communication would also experience evolutionary adaptations. In the vastness of space, effective communication over immense distances and amidst potential electromagnetic interference is critical. Humans might evolve enhanced auditory capacities, capable of discerning subtle acoustic signals amidst background noise, or even rudimentary electromagnetic perception, enabling direct communication through bioengineered implants interacting seamlessly with neurological pathways. Imagine conversations occurring directly through neural impulses, eliminating the delays and misunderstandings of traditional verbal communication, a radical step forward in collaborative space exploration. Environmental perception in extraterrestrial settings, vastly different from Earth's, might also push evolutionary shifts in human senses. Humans could develop an acute sensitivity to environmental cues, temperature fluctuations, air composition changes, or subtle vibrations within spacecraft or planetary habitats. Skin receptors could evolve heightened sensitivity, becoming finely tuned to detect environmental abnormalities instantaneously, alerting individuals to potential hazards before they become critical, significantly enhancing survival rates in off-world conditions. Space habitats themselves could catalyze evolutionary changes in human social behaviors. Isolation and close living quarters demand harmonious interactions, and future humans might inherently exhibit reduced aggression, heightened empathy, and robust cooperative tendencies. Evolution might favor neurological pathways that prioritize conflict resolution, altruistic behaviors, and enhanced emotional intelligence, ensuring the success and stability of long-term space colonies. These social adaptations could lay the foundation for a deeply interconnected, cooperative civilization thriving amidst the harshest environments. Finally, perhaps one of the most remarkable evolutionary transformations involves longevity. Space travel across interstellar distances necessitates significantly extended human lifespans. Future humans could evolve dramatically slowed cellular aging processes, bolstered by enhanced DNA repair mechanisms and resistance to oxidative stress. Genetic modifications might introduce elements from extremophile organisms capable of longevity under extreme conditions, resulting in humans who age far slower, living far longer lives. Such unprecedented lifespans would enable humans to embark on interstellar voyages spanning multiple generations, fundamentally redefining humanity's temporal horizons. As humanity steps further into the cosmos, these evolutionary changes aren't merely speculative fantasies. They represent plausible pathways driven by real-world biological mechanisms. By leveraging advanced biotechnology and genetic engineering, humans could deliberately accelerate their evolutionary adaptation, guiding it toward beneficial outcomes essential for thriving in space. Each evolutionary adaptation brings us closer to a future where humans, fundamentally reshaped by space's unique demands, navigate the cosmos with unprecedented ease. This next chapter in human evolution will not merely alter our physical form, it will redefine our very identity, values, and aspirations. The stars no longer represent distant, unattainable dreams but become realistic destinations for humanity's continued growth and exploration. Ultimately, evolving for space travel signifies humanity's resilience and boundless ambition. As our bodies adapt to the cosmos, we will forge a new era of exploration and discovery, transcending our earthbound origins. This remarkable transformation reflects humanity's enduring quest for survival, growth, and understanding, carrying us forward into a thrilling, limitless future among the stars. As we venture deeper into space, we do not merely explore, we evolve, forever changing what it means to be human.